What's up? My name is Matthew, and in this video we're going to talk about exponential functions. The first thing we need to know is generally what does an exponential function look like? And in this blue box we see function notation being used as well as regular y equals notation. And on the right hand side of these equations we see b to the x. And here we're being told that the b value is a constant, so it's not a variable, it's just a number that we don't know what it is yet, but it's an undisclosed constant, and it needs to be greater than 0, but it can't be 1. And the advantage to working with these is that they are perfect for describing certain types of phenomenon. And some examples using different function names, we're seeing f of x and g of x and so on. Remember that those are function notation. It does say f of x, that does not say f times x, it does not say h times x. X is our independent variable, and f and g and h and j, those are the names of our functions. And we see different bases, 2, 10, 3, and then the j function has a base of 1/2. Still a positive number, greater than 0, still doesn't equal 1. And we're going to see that if we have a base that's between 0 and 1, or a base that's greater than 1, especially graphically, we're going to see some different results. Here's an illustration of the result of choosing a different base. So in blue, you're seeing what happens when we graph an exponential function that has a base greater than 1. So you see there it's labeled f of x equals b to the power of x, and the fact that x is in the exponent position, that's what really makes this an exponential function. So when b is greater than 1, our curve as we go from left to right is going to have y values that are increasing. And in red, you see what happens visually, graphically, if we have a base that's between 0 and 1. As we go from left to right, our y values decrease. Never do our y values reach 0. There's no way to take a number, a positive number, and raise it to a power and have the result be 0. You can get it awfully close to 0, but it's never going to quite reach 0. Also remember something that you do know that you've heard before, is that if you take a number or even an expression and you raise it to the power of 0, the result is 1. And that's why we're seeing both of these graphs crossing the y-axis at 1, because that's where our x variable is equal to 0. And if we're taking a number and raising it to the power of 0, the result is going to be a y value of 1. So all of these initial graphs that we see are going to have y-intercepts of 1. The domain is all real numbers. That's hiding behind me in number 1. We see that the domain is all real numbers. You can have any number in that exponent position that you want. Number 2 comments on the y-intercept being positive 1. Number 3 is talking about the graph in blue, where our base is greater than 1. Number 4 is the graph in red, where our base is between 0 and 1. Number 5 tells us that both of these functions, all of our exponential functions, are 1-to-1. And what that means is, well, let me ask you this first. Look at the red function and the blue function for that matter, but one at a time, and tell me, are those curves, are those graphs, the graph of a function? And the answer is yes, because they pass the vertical line test. It's not possible to draw a vertical line and have it intersect our red curve at more than one point. Nor is it possible to draw a vertical line and have it cross our blue curve at more than one point. Therefore, both of these graphs are the graphs of functions. Now, if we found the inverse of both of these functions, would the result be an equation that's also a function? And the answer is yes. We can determine that by using the horizontal line test. Since it's not possible to draw a horizontal line that crosses my red curve at more than one point, I know that its inverse graph is going to be the graph of a function. And the same thing holds true for the blue curve. When a function has an inverse that's also a function, we say that that function is 1 to 1. And that's what we're seeing is being written here in number 5. Exponential functions are 1 to 1 functions because they have inverses that are functions. And we see in number 6 that the graph of b to the x approaches but does not touch the x-axis. Therefore, the x-axis where y equals 0 is a horizontal asymptote. In other words, our y values are always going to be positive until we start shifting these curves around. But at least initially, we're going to be staying above the x-axis. And this first example asks us to graph the function g of x, which is equal to 4/3 raised to the power of x. And it's recommended that we graph this function by making a table of coordinates. So I came on ahead and started writing up a table. And in the left-hand column, I've got my x values. And in the right-hand column are my y values, my g of x values. So x comma y, that's why I put the x's in the left-hand column. And I just chose some x values that were near 0. I started at 0, you see it in the middle there. I picked 3 to the left and 3 to the right of an x value of 0. And on the bottom half of this table, I've already started generating some y values. With an x value of 0 plugged into our function, we have 4/3 to the power of 0. And as we talked about already, anything to the power of 0 is equal to 1. So you see our y value of 1 there. And then if we take our x value of 1 here and we plug it into our function, we get 4/3 to the first power. Anything to the first power is itself. So there's our y value of 4/3. And then we plug in an x value of 2. Now we're taking 4/3 and we're squaring it. And to square the fraction, we are multiplying the fraction by itself, 4/3 times 4/3. So in the numerator, you've got a 4 times 4, which makes a 16. In the denominator, a 3 times 3 makes a 9. So you see my y value of 16/9 next to the x value of 2 there. And so on into number 3, we're cubing the numerator and denominator. And we'll plot some points in a moment. But these other x values, we worked with an x value of +1. How is the result going to be similar or different to when we have an x value of -1? Remember that the x values of -1, -2, and -3 are getting plugged into this function, and those x values end up in the exponent position. And when we have a negative in the exponent position, it tells us to do something very specific. Just the negative part of that exponent tells us to take the reciprocal and then apply the rest of the exponent, the 1, the 2, or the 3. So when I apply, I'm going to start actually at the top with the -3. -3 says, take 4/3 and take its reciprocal, and then cube it. Or you could do those two things in reverse. You could take 4/3 and cube it, which would give you 64/27, and then the negative sign tells you to take the reciprocal, which flips the fraction 64/27 and gives us 27/64. So it's nice that we've already figured out the positive exponents because all we have to do is take the reciprocal and put them into their corresponding negative exponent positions. So where x is equal to -2, the result will be 9/16. And at -1, we will have 3/4. And then let's plot some points. Let's take it from the top. -3, so I'll come left 3 boxes, and 27/64. What's 27/64? I have no idea. Let's see, 27 divided by 64 gives me 0.42. So I probably should choose a different scale, but instead I'm just zooming in. So I've got 0.42 with an x value of -3, so just below a half. I've got a dot there. And at -2, I'm at 9/16, which is a little bit more than 8/16, which is 1/2. So at -2, we're a little above a half. And at -1, we're at 3/4, so we're getting close to 1 there. Oh, and there we are. When x is equal to 0, we've got a y value of 1, so we're crossing the y-axis. At 1, we go to 4/3. At 2, we're at 16/9. Keep a 4-function calculator nearby so that you can get a feel for what these numbers are. 16/9 is 1.777 repeating, so more than 1.5. And at 3, we're at 64/27. That is 2.37. So a little more than 2 1/4. And I think you can see that as we go from left to right, these points that we're plotting have y values that are trending upward. So our curve is going up. And so that we can have a really good sense of what this looks like, I went into desmos.com, desmos.com, and I typed in this equation. And in fact, I didn't even put in the y equals, and it accepted it. Let's come in and drop in the y equals. We get the same curve, y equals, and there are parentheses right at the bottom of the screen. You can see the parentheses there under the x and the y. So put that 4/3 in parentheses to make sure that your exponent of x gets applied to the entire value of the fraction, and then you see the resulting curve, which looks a lot like the one that we just graphed. And at the y-axis, if you click on that point that's there, the coordinates show up, and indeed 0, 1. So we have done that correctly. We're crossing the y-axis with a y-intercept of 1. All right, let's hop back over to the notes. And if you want to, if you are graphing this on your own, you're welcome to freehand a curve through here. Mine's probably going to be rough. I don't have the steadiest hand, but something like that, all right, curving in the upward direction. Let's see what else we have that hopefully doesn't require me to draw any brilliantly smooth curves that passes through 6 different points, all of which are really close together. Here we go. Transformations of exponential functions. Now this word transformations is something that you've worked with when you're talking about the graph of an absolute value function, or a parabola, or a cubic, or a square root function, maybe even a cube root function. This is where we're shifting our graph upwards and downwards, left, right. We're reflecting over the x-axis and the y-axis. We've got shrinking and stretching that happens. All of these processes are the same as what you've experienced in transforming other functions, other graphs. Works exactly the same way. And when I say exactly, I mean exactly the same way. It shows up a little bit differently because the modifications, the transformations that we make, aren't just happening inside parentheses or inside the square root function. Now it's a little unusual looking because they're happening in the exponent position. Now in this first column, or sorry, this first row, we're seeing a plus c and a minus c. And that addition and subtraction is happening after we've taken our base and raised it to the power. And those kinds of modifications cause a vertical shift, either upward or downward. If it's positive, it goes up. If it's negative, it goes down. Now, if we make the same, very similar kind of a modification, but we put those modifications in the exponent position with the x value, now it's not a vertical transformation. The modification is happening in there by the x variable, so that's a good clue that it's going to be modifying in the horizontal direction, the x direction. And as has been the case with every other function that you've transformed, if you add something to the inside of the function, it shifts in the negative horizontal direction. And if you subtract something inside the function, it shifts in the positive horizontal direction. So it's counterintuitive. Just be careful with your modifications inside the function. Reflections, A negation outside the function flips you over the x-axis. And if there's a negation inside the function, in the exponent position, then you get a reflection over the y-axis. Anything that was to the left is now to the right. Anything that was to the right, now it's to the left. Vertical stretching and shrinking. If we multiply by a constant value outside the function, the result that you get is going to be what you would expect. B of x was the original generator of y values. And we're taking those y values and we're now multiplying them by c, some number. So if you multiply by 3, you're tripling all your y values. So your y values are going to get higher and lower. If you had a y value of 5, you multiply it by 3, now it's 15. The x value didn't change, but the y value sure did. And maybe you had a different point that had a y coordinate of -2. Well, if you multiply that by 3, now it's -6. It's much farther below the x-axis. So it causes a vertical stretch, as though you've grabbed the top and the bottom of it and you're pulling it upward and downward, okay? Pulling the top part up and the bottom part down. Vertical stretching. Now, if your modification happens by multiplication inside your function, then you're modifying the x value. So it's not a surprise that your horizontal stretch or shrink is going to happen in the x direction. However, it's again backwards from what you might expect. If I multiply, in this case, my exponent x by 2, if my c value is a 2, then my graph actually gets horizontally shrunk. And that's like I'm pushing in on it from both sides. I'm compressing it, okay? If I multiply by 2, the graph becomes half as wide. If I multiply by 3, it becomes 1/3 as wide. Now, if I multiply by 1/5, if I multiply by 1/5, my graph becomes 5 times wider. And I mean in both directions. Just as my horizontal shrink was a compression from both sides, if it's a horizontal stretch, then I'm going to pull it in the left and right directions, both of them, okay, by some multiple. So let's check out an example question. This one is starting us off with a parent function, an exponential function, f of x equals 4 to the x. And then there's this modification, this transformation made down here. We've added 1 to the inside of the function, inside the exponent position. What's the result of that? Well, we're adding it to the x value, so it's going to change something in the x direction. It's addition, so it's going to be a shift, but because we're actually modifying the x value inside that exponent function, exponential function, the result is going to be backwards from what you think. You'd think that this would shift us 1 unit in the positive horizontal direction, to the right. However, it does not. The +1 moves us to the left 1 unit. However, this -1 that's on the outside does modify our y values the way you would think. It does drag the graph down 1 unit. So we're doing a horizontal shift to the left 1 and vertically down 1. Left 1, down 1. Option B it is. You know what? Before we talk about the natural base of e, let's just come up with one more quick example. What if we had a different function, h of x, that was equal to, let's use 3 to the x this time. And then our new function, j of x, is equal to, how about -3 to the 2x plus 4. There are a bunch of transformations happening here. Which one should we apply first? What am I supposed to do? I see 3 different things. There's the minus sign, the negative sign. There's the multiplication by 2. There's adding the 4. I would always do my reflections and my horizontal and vertical, so both. So I would do my reflections and my stretches or shrinks first and save the shifting till last. So the negative that's on the outside of this function is going to reflect us over the over the x-axis because it's negating our y values. So this as number 1, and then we'll address the 2 second, and we'll address the 4 third. The first thing that happens is a reflection or a flip over the x-axis. The second thing that happens, we're multiplying by 2 in the function. We're in the mix there, in the exponent position. Multiplication by 2, it's modifying the x, so it's going to be a horizontal kind of a transformation. It's going to be either a stretch or a shrink. Is this thing going to get twice as wide or half as wide? Don't forget that when you're inside the function, you're going to get results that are the opposite of what you think. It's not a horizontal stretch by a multiple of 2, it's a horizontal shrink. We're going to be half as wide as we were before. So this is going to be an h for horizontal shrink by 1/2. Or write that however you want. The resulting graph will be half as wide. And third, the +4 is a vertical shift in the positive direction, 4 units. You could just write up 4. Right, so I just wanted to look at a couple of other types of modifications, so I'm glad that we went through and looked at that, and now we can move down here and talk about the natural base. I wouldn't write any of this down maybe, except that the natural base is called e. E is a letter that represents a number, just like pi is a Greek letter that represents a number, and the lowercase I represents the imaginary constant square root of -1. Here, lowercase e is now representing this very unusual decimal. This decimal, you're seeing it here, so this I would write down also. And the squiggly equal sign means approximately equal to. And e does end up being equal to approximately 2.7. Where does it come from? Oh, it comes from this formula. When you make n really, really, really big, the resulting decimal gets closer and closer to e. And that's a conversation you could have again in a elementary calculus or a Calc 1 class. It's an irrational number because it's a decimal that's non-terminating and non-repeating. Goes on forever and never repeats. It's called the natural base, and f of x equaling e to the x, is called the natural exponential function, which transitions us into the subtopic of compound interest. And this little subtopic is going to build to a point where we bring e back into the conversation. So the idea of compound interest is where you earn interest on interest that you've already earned. That sounds like a pretty good deal to me. You're going to give me interest, and then I let you hold on to that money, and then you'll pay me interest on the interest that you gave me? Yes, I'm in. We're going to see some variables here. The capital P represents principal. You could write that down. At the end of the accumulation of interest, however frequently you're getting your interest, the final amount that you walk away with is your accumulated value, and that is going to here be represented by capital A. Your interest rate is going to be represented by lowercase r. It's mentioned here. Here they're calling it an annual percentage rate, okay? And that's fine. And that r value is going to go into this these couple of formulas that we're going to look at. It's going to go in as a decimal. So if it's 5% interest, r would equal 0.05. Again, 5% interest means 0.05 for an R value. If your interest rate is 12%, then R equals 0.12. All right, so we've got to account for 2 digits after the decimal point there. If you're getting paid interest twice a year, we say that you're compounding your interest semi-annually. If you're getting paid interest 4 times a year, there are 4 quarters in a whole, so you would say compound quarterly, and then you can compound your interest more and more frequently, monthly, daily, every minute, every second, to the point where you end up with n compoundings per year. If it's compound annually, your n value is a 1. If it's semi-annually, twice a year, your n value is a 2. If it's quarterly, your n value is a 4. 4 quarters in a whole. Monthly, n is 12. I'll stop there before I drive you mad. But be aware and put into your notes also that n represents the number of compoundings per year. I'm going to move right through that. I'm going to move right through this topic of conversation. This is where we're taking one formula and we're making our n value very large as n goes toward infinity. What comes out the other side is a sort of a mutant formula, p times e to the rt. And the reason I'm kind of just touching on those briefly and then getting to this page is so that you can see the 2 formulas side by side. Number 1 is when you're compounding your interest n times per year. Annually, semi-annually, quarterly, monthly, daily. For daily, you would have an n value of 365. But if you can manage to compound a million, billion, write all of the zeros, times per year, we call that compounding continuously. And that mutant formula that I mentioned before is often referred to as the PERT formula. P still stands for principal, A still stands for your accumulated value, R is still your interest rate as a decimal, and T measures time in years. So if somebody says calculate the interest in 6 months, be careful, your T value needs to be 1/2 or 0.5. And that's written here. T is measured in years, so make sure that goes into the notes along with what N represents, what R represents, P, A. Make sure T is in there. And then let's try example number 2, and I believe that's the last of our notes for this section. So let's see what we end up with here. Find the accumulated value of an investment, $5,000, that's our principal. For 10 years, that's our time, at an interest rate of 6.5, that's going to be our R value. Compounded semi-annually, that's 2 times per year. So part A, semi-annually, our accumulated value is going to equal our principal times 1 plus our interest rate divided by the number of compoundings per year raised to the power of number of compoundings per year times number of years. And in the problem that we're working on, our principal is 5. You could keep going left to right. I'm going to go vertically on this one so that everything kind of lines up and you can see it kind of matching up. The P is the $5,000. That's your principal. This 1 represents you getting back 100% of your money. And that's the plus sign. 0.065, that's my interest rate as a decimal, divided by the number of compoundings per year. Since it's semi-annually, that's going to be a 2. And then we'll raise this to the power of 2 times the number of years, which was 10 years. Now, if you have to type this into a calculator and you only have a 4-function calculator, it's not good. You can't do exponents on a 4-function calculator. If you have a scientific calculator, it depends on which one you have. If you have a TI-30XA, which is a single line entry calculator, this is going to be challenging. If you, I don't think I have my scientific calculator here. Oh, I do. All right. So if your calculator looks like this, that's the TI-30XA, I will tell you that the first thing you should do, so if you don't have a TI-30XA and you don't have a single line entry calculator, you don't have to write this down. But if you do, this might be valuable to you. The first thing I would do is calculate this. Okay, let's figure out what 0.065 divided by 2 is. Once you have that answer on the screen, well, let me just do this with you. 0.065, yep, divided by 2 equals 0.0325. Okay, I'm going to leave that number on my screen. I'm holding my calculator. It's down here. And then I'm going to do the plus 1. So however you want to note that, maybe like this. That's the second thing I'm going to do. Or you could just put an arrow pointing to the plus 1. That's the second thing that you're going to do. So I'm leaving this number on my screen, and I'm just hitting plus 1 equals. Now it says 1.0325. Great. And then take note of the fact that this is equal to 20. So I'm going to take this number that's on the screen of my calculator, and I'm going to raise it to the 20th power. Now, how do I do that? On this calculator, there's a button in the right-hand column, and I'm sorry that you can't see it. You could make it a little bit bigger, I suppose. This button on the right-hand column says y to the power of x. Sometimes you'll also see that button if you look to the right of me here, to the right of the calculator. You'll see a button that just looks like kind of an upside-down V. Maybe you call it a caret. It's the same symbol that's above the number 6 on the keyboard on your computer. And we often use that to represent putting something into the exponent position. So I'm going to hit that button, and then I'm going to make myself small again. And then I'm going to type in the 20, and then hit equals. So I had the 1.0325 on the screen. I hit the y to the x button. Then I typed in the exponent 20, and then I hit equals. And now I've got 1.8958, blah, 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 blah. I need to take that number, which is all of this stuff. I've covered all of that, and I need to hit times 5,000. Times 5, 1, 2, 3 zeros. And now I have 9,479.189. You'll probably want to round that to the nearest penny or maybe to the nearest dollar. All right, again, 0.19 rounded. Okay, that's on a single line entry calculator, and that is a pain. Okay, a 2-line entry calculator, I think it's called a TI-30, maybe it's even the XA2, Roman numeral 2. You could just type this thing in from left to right exactly as it appears, using parentheses, like I said, exactly as it appears. It's the same way that you would type it in if you were typing it into your graphing calculator. All right, just type it in from left to right. 5,000. I'll just articulate what it is that I'm typing into the grapher. I'm on my home screen where I can just do basic arithmetic. I type 5,000, and then I open a parenthesis, 1 plus 0.065 divided by 2, close parentheses. Oh, this calculator actually has the caret on it, that little upward V, or upside down V. So I hit the caret. It puts my cursor into the exponent position on this calculator. And then you could type 2 times 10 if you want to. I'm just going to type 20 and hit enter. And I still got the same value, 9479 approximately 0.19. All right, it didn't give me in as many decimal places. That's a setting that we could change. All right, so that's a little calculator tutorial. I did not write down whatever the answer was to that question. Sorry. Here it is. Oh, I'm writing with a highlighter. Equals. Approximately, you could put the squiggly equal sign if you want. 9479 approximately 19. All right, that's quarterly. Now, if we want to figure this out, or sorry, that was semi-annually. Part B asks us for quarterly. So now, our accumulated value will be calculated by taking the $5,000 principal, multiplying it by 1 plus. We're going to take the interest rate, 0.065. We're going to divide it by 4 because it's compound quarterly. And in the exponent position, we'll do 4 compoundings per year times 10 years. And you can run that into your calculator. I'll tell you what I got as a final answer. That's a 4. That becomes a 40. Enter. I got 9,527, so $9,527 and approximately 79 cents. You could go through the same motions to compound monthly. So I'm going to skip part C. I'm going to jump to part D. So for continuous, the equation looks drastically different. Here, A is equal to P times E to the RT, which is, I'm going to go left to right on this one, that's $5,000, times E, which is a number already, to the power of, our interest rate as a decimal was 0.065, and we'll multiply that by T, which is still the number of years, which is 10, and then I'm into my calculator. Let's do this one on the scientific calculator also. That's the more difficult one to type into. So I'm turning it on. I've hit clear a couple of times. And I'm going to realize that my exponent is equal to 0.65. If you take 0.65 and you multiply it by 10, you're going to get 0.65. So that's your exponent. Now, you'd think that the next thing you might want to type in is e to the power of 0.65. You're right and you're wrong. On this goofy calculator, we're going to type in the exponent first. So I'm going to type 0.65. Now make sure you started with a 0 on the screen. I type 0.65 and then it's on here somewhere. Above the natural log button in yellow, you might be able to read it. It says e to the power of x. It actually says e to the x. I need to engage that feature, but because it's above the natural log button, I'm going to hit this button over here that says second, and then I'll come over here. Can I do this in the mirror? And I'll hit this e to the x button, and you saw that the number changed on my screen. It's a very lousy looking number. I got 1.91554. Right, and that's e to the 0.65. Now I'm going to leave that number on the screen because that's a decimal that goes on and on and on right off the screen. And I'm just going to hit the multiplication button times 5, 1, 2, 3 zeros, 5,000. And I get a final answer of 9577.70. So you can see when we compounded semi-annually, I didn't realize that I was still full size there. When we were compounding semi-annually, we ended up with an accumulated value of 9,400 and change. Compounding quarterly, we made it up to $9,500, $95.27, and then by compounding continuously, we got out a little bit more money, like an extra $50 or so. It went up to $9,577. Now, if the principal were larger, then the difference between those answers would be even larger. And that would be an even better illustration of just how valuable compounding continuously is compared to any of the others. All right, one section down, you'll see my face and this t-shirt in another couple of videos if you're going to hang with me. If not, I will see you around, but otherwise, if you're one of my students, my guess is you're probably clicking into that next video real soon, so I will see you real soon. Thanks so much.